Okay, we are formally recording now. So I'll go ahead and get started, Alan. Welcome everyone to our session today. I appreciate everyone joining either in the morning, afternoon, or evening, wherever you are, wherever you happen to be in the world. Welcome to our session today for computer vision for Cohere for AI. And for those of you who are new, just a quick overview of Cohere for AI. Cohere for AI is a nonprofit research lab that seeks to solve complex machine learning problems. And we do this by supporting fundamental research that explores the unknown. And we're focused on creating more points of entry for those who are interested in machine learning research. So we do that a number of ways, but one of the main ways we do it are with sessions with researchers such as Alan Chang, our guest today, who are experts in certain aspects of computer vision. So with that being the case, I'd like to introduce our guest today. Our guest speaker today is Alan Chang. Alan is an incoming PhD student at University of Penn NLP. Previously, or just recently, he completed his bachelor's in computer science at University of Southern California. And his interests in terms of machine learning are in language grounding, social inference and reasoning, and learning from synthetic data. So with that being the case, I'd like to go ahead and segue to you, Alan. Go ahead, take it away.
Yeah, thanks so much for the invite. And yeah, this project deals more with learning from synthetic data and issues of fairness and social inference. So I'm excited to kick this off. Let me see if I can share my screen.
Okay.
Okay. Can you guys see my screen all right?
It's coming up now. Okay, we can see it now.
Okay, perfect. Yeah, so jumping right in, I'll be presenting a project on fair facial recognition from diverse synthetic data. And specifically, we're exploring debiasing facial recognition classifiers by trying to sample diverse synthetic data using a type of optimization called quality diversity optimization. And we call this method quality diversity generative sampling, or QDGS for short. Title's a bit of a mouthful, so you can ignore it for now. But by the way, if you have any questions, feel free to shout them out whenever. Yeah. Before diving in, I kind of want to share a story that relates to this project and more broadly facial recognition tech. I recently graduated from USC, and pictured in the center is our USC Village, which has a lot of shops for food, groceries, and more. I used to eat here a lot. Nearby there's Pot of Cha, one of my favorite boba stores. And there's also Ramen Kenjo, which I used to buy soup from a lot when I was sick. And around 2022, there was this payment service, a new one that started appearing up in Pot of Cha and Ramen Kenjo, among other shops, using facial recognition technology. And it was called Pop Pay. I think if I remember correctly, the slogan was pay with your face. I think the exact language of the slogan might be wrong here, but it was something of similar meaning. And I thought it was really interesting because I feel like faces can look so similar, and tying it to something more sensitive could be, I don't know, I was kind of skeptical. For one reason or another, I think Pop Pay started becoming really popular at USC. The stores would start to give you discounts or credit if you paid with your face. And in the fall at the Welcome Back concert, you even had to use it exclusively to pay for your food. So at this time, I'd already started doing a bit of ML research, and I was kind of skeptical about the accuracy of the service. What if Pop Pay falsely predicted that I was the buyer when really it was someone else who was trying to make the purchase? And so I tried to remove my credit card from the service, but it told me I had to have one on hold. And long story short, I was eventually able to remove myself from the system, as far as I know. But it was annoying, and it was a pretty scary situation. I think the situation kind of scared me because I didn't really have confidence in the technology to protect users of malicious attacks, which more or less there's always going to be attackers. And there's also unintentional harm when predictions aren't accurate, which is also always bound to happen. And I share this story because, for better or for worse, there's an increasingly high amount of applications where facial recognition has sort of become the de facto accepted tool for identity verification, whether it's in security or law enforcement or e-ticketing and immigration. And it's kind of scary, and this technology has a lot of possibility for maluse, specifically with mass surveillance. But because it's sort of just become so widespread, there are really important issues of fairness to consider. And this sort of experience was one of the inspiration points for why I was interested in digging into this project. The issue with training these facial recognition models is, like most ML models, they're trained from data that are often lower in diversity than we'd like. So if we look at some popular facial data sets and plot the skin tone proportions, they sort of repeatedly lack dark skin representation. And skin tone is just one of the axes or concepts of diversity that we might care about in this application. Really, there's many concepts along which the data sets are underrepresented, usually due to some sampling selection or internet biases. So in this project, we're curious about the alternative types of data that can substitute the lack of diversity in real data that is able to be collected. Recently, as you guys all know, generative AI models are able to substantially generate very realistic data for numerous modalities across different architectures, GANs, diffusion models, language models. More than ever, there's interesting research questions of when and how we can use generative AI to help create quality and diverse synthetic training data sets. And so in this work, we're tackling like a pretty specific area. We're looking at debiasing skin tone bias using facial image generators. This isn't a really easy task, however. These generators are often trained on real data sets that are biased in many different ways. One might be skin tone, one might be gender presentation, among a lot of other things. And as a result, the mappings that they learn can be biased and their distributions may collapse on dominant classes or attributes. Mode collapse can be pretty difficult to see from a single data output, but when looking at the entire distribution, we can look at patterns or attributes that are consistently underrepresented. So I plotted this figure to show the output distribution of StyleGAN2, one of the more popular facial image generators when this work was done. This version was trained on a data set called Flickr Faces HQ, Flickr being the online platform where you can upload your own images. And for some reason, it was made into a data set. And now there's a lot of training data for generating high quality faces. The issue, as we saw in previous slides, being that there's a lot of imbalances in Flickr Faces HQ still. These sample and density maps are projected onto a clip latent space, which means that each of these images are mapped onto a specific point on this axis based on its similarity score to a text prompt. So this text prompt could be a masculine person, a feminine person, it could be hair length. And looking at the density map, we see that this range of skin tones is actually quite narrow. Additionally, StyleGAN2 inherits the skin tone, or it inherits the skin tone bias from the data set, which was very skin tone imbalanced. Additionally, we see this bimodal distribution on the left here with respect to traditional binary gender presentations. And there's also single dominant modes for skin tone, hair length, and age. When we're using this data, the synthetic data for pre-training, classifiers can inherit these biases. And there's not really an effect on fairness, especially because the synthetic data is so imbalanced, just like the real data. So given that the outputs of the synthetic data are very biased, we want to explore, can we use these bias generators to sample some sort of helpful synthetic data for the task of debiasing or for the task of fairness? With large generators, we can try to use sample optimization algorithms to help to generate synthetic data sets that are better than just random sampling. In these algorithms, often diversity can be expressed as just distance in latent space. I've seen this more frequently in lower stakes generation, such as with stable diffusion and ImageNet classification. And while distance in latent space can be a helpful heuristic for diversity, we don't really know in which ways the outputs are actually diverse. So distance and latent space by itself isn't really a satisfying method to protect diversity in our synthetic data. For example, if a generator is susceptible to mode collapse, it's possible that even if latent vectors A and B are a large distance apart, the model mapping might not be surjective, and these 2 points might produce a very similar image or even the same image. A more popular approach, particularly in facial recognition, maximizes a single factor objective function. So this objective can be estimated with a skin tone classifier, for example, a dark skin tone classifier. And by iteratively optimizing over dark skin tones, the sampling algorithm can search for more images of faces with dark skin tones, and then you can have a synthetic data set that has a more balanced proportion of skin tone. However, single factor optimization can kind of get stuck at local minimum, and it's not very helpful for generating intersectional data, which is simultaneously balanced across multiple concepts. And so large generators are often capable of generating these mix of underrepresented output features, such as dark skin tones and eyeglasses, but these inputs are difficult to find in latent space because they're so rare in real data. So we want to find an optimization algorithm that can simultaneously bring all these underrepresented features out. Our approach is to use a type of evolutionary optimization algorithm called quality diversity. And essentially, quality diversity is a type of optimization algorithm that tries to find multiple high quality and diverse solutions to an optimization problem rather than a single high performing solution. So imagine in like a robotic scenario, you might want to find high performing policies to complete an obstacle course, but for different robot embodiments and energy constraints. And so if you're able to generate a high quality solution across these different diverse criteria, then you have this set of solutions that you might be able to use in this application, which is pretty helpful and stronger than just a single high quality solution. In the application of learning from synthetic data, we want to have clear images, but also diverse across different concepts of interest. For facial recognition, this might be skin tone or facial pose, lighting, and more. But thinking of an exhaustive list of these concepts that you want to be diverse across can be kind of a challenge. So that's one of the limitations of trying to balance everything all at once. It's really difficult to figure out what you actually care about all before pre-training. So it's still pretty nice that we're able to define specific criteria that we might like using text prompts though. And so I'll go more into depth about how this works in the next slide. QDGS, it's an iterative algorithm. So each iteration will add data to the synthetic data set. Actually, I might pause over, actually I'll go 2 more slides and then I'll pause for questions. But QDGS is an iterative algorithm, so each iteration will add data to the synthetic data set. Each iteration of QDGS has 2 main parts. In the first part, steps 1 through 4, we want to describe the image's quality and diversity concepts using one objective function and multiple measure functions. So in step 1, we have a latent code data, and it's mapped to a corresponding output image. In step 2, we want to compute the quality of this image using an objective function. And for this application, we chose the objective function to be a linear combination of 3 heuristics. The first uses similarity to a text prompt, similar to how we projected the images onto the clip latent space previously. The second uses a latent distance margin, similar to prior work, where we want to maximize distance and latent space. And then the third is a regularization penalty to constrain codes from being a part of the training input distribution. Otherwise, the images can kind of end up looking wacky. There could be like reddish hair or yellow teeth, which in some scenarios, that might be helpful. But in other scenarios, if you want the data to be more realistic or within a smaller group of the training input distribution, you might want to increase that regularization penalty. Step 3 is the important part. This is the part where we express the different concepts that we care about for diversity. So these will be controlled by different measure functions, and we implement the measure functions using the clip scores to text prompts. So whether the image is similar to the text prompt, this is an image of a masculine person or a feminine person. This person has light skin or dark skin. This person has long hair or short hair, and other things that you might care about in this application. In step 4, we update the archive, which is like the data set that we're trying to build, and we compute the improvement of the objective score for each cell of this measure space. Okay, so to summarize part 1, we're essentially generating the output image, and we're scoring the image for how much quality it has, how much, what space in this measure space it is located in, mainly using text prompts, which makes this more customizable for different applications. Okay, so we've generated the image, we've computed scores for how much quality it has, where it lands in this measure space. Next, we want to mutate the images so that we get different types of images in our data set. And so step 5 applies gradient ascent to maximize the objective function. This way, while we iterate over this process, we're getting images that are higher in quality according to the objective function. Steps 6 through 7 are an evolutionary optimization step, and they're mutating the images by branching it along objective measure gradients ranked by the improvement that the images were able to gain in that particular cell in the measure space that it lands on. And so if you're curious about the math, I recommend reading Matt's CMA May paper, which I've added onto this slide. But in essence, it's looking at how the measures relate with each other and how to best explore the remaining space in an iterative process. Okay, I think this is a good time to take a pause. Are there any questions so far?
I don't see any in the chat so far, Alan. If anyone has any questions at this point, you can bring yourself off mute to ask the question. I think we're okay at this point, Alan.
Okay, sweet. Okay, so we first tested this on a smaller, simpler proof of concept domain, which we call the colored biased shapes. And we created a real data set of shapes where the color of the shape was biased at different levels. In these experiments, we generated the data sets with 1,000 samples, and then we trained shape classifiers on these data sets, repeated for 5 trials, and finally we evaluated for accuracy on a balanced test set. So there was no bias in this test set. This is what the data set sort of looks like. The real data set consists of either triangles or squares. And we generate 5 versions of this real bias data set where B proportion of the data are red triangles and or the blue squares, and 1 minus B proportion of the data are blue triangles or the red squares. So there's this majority group. You're either a red triangle and a blue square, or you're part of the minority group, the blue triangle or the red square. And this sort of confuses the classifier because it spuriously associates the color with the shape. For the generator, we trained the autoencoder on the version with 98% bias. So the majority group takes up 98% of the data set to get a strongly biased generator. When we sample from this bias generator, as expected, looking at the sample map on the left, the generator associates color with shape. So we see that the triangles are more often red and the squares are more often blue. At the same time, the generator isn't trained super well, and there's splatters of colors that aren't really shapes. Traditionally, in a larger, more well-trained GAN, we might call these out of distribution because the input vectors aren't producing images that are of the output distribution. On the right side, we're trying to use quality diversity generative sampling, which is better able to sample shapes more uniformly across the measure space. And so we ran QDGS with an objective that was optimizing for text prompts of shapes, and then it was penalizing for negative text prompts of like splatters of colors. And then our measures were either red or blue, and then square or triangle. When we use the data set on the right for training, we find a large improvement for shape classification. As expected, the improvement is greater at higher bias levels. And when the bias level is less, the improvement is smaller. This is pretty cool because even though the generator is biased, the real data set is biased, we're able to improve performance substantially with QDGS. And so we're curious whether these results will hold in a more difficult domain in facial recognition. So shifting gears, we ran experiments with synthetic pre-training data sets of size 15,000 images or 50,000 images. And then we pre-trained and then trained facial recognition classifiers on these data sets, repeated for 10 trials. And then we finally evaluated for fairness and accuracy. In these experiments, the training data set was Casio WebFace, and then the pre-training was either none, or the randomly sampled, or the quality diversity. We're going to first look at the distributions, which I think are really interesting to look at. So on the top is the previously the distribution that previously appeared with StyleGAN2 when we were randomly sampling. So we see the similar modal distributions. We see that the range of skin tones is a bit narrow. Conversely, with quality diversity, we see that the range of outputs has sort of increased, and this increase is sort of more substantial for skin tone and hair length. It's less noticeable for gender presentation and age, which is kind of interesting. There's also these sort of weird associations that you see between concepts. On the bottom left density plot, we can see that the dark skin tones are more associated with masculinity, and then the light skin tones are more associated with femininity. And I think this association is possibly representative of like the sample of images that were uploaded to Flickr. It's also possible that it's just the way that images are captioned on the internet. These image text pairs might be represented in this way in a clip, and that's how it's being projected. On the right-hand side, there's some sparsity for people with long hair that appear younger, likely because young people don't really have long hair as often. So there's sort of these associations that you can kind of see whether they're generated from, they're part of the generator or the way that we're mapping the images onto these projections. Overall, though, it's pretty nice that we're able to see that this sampling algorithm is able to get a larger spread of these concepts that we might care about, and not super like narrow modal distributions that come from random sampling. Okay, so let's try to eliminate clip out of the picture because there might be some linguistic biases with clip. Over here, we are looking at the categorical labels that appear in some facial data sets. So we trained some classifiers to predict skin tone, age, gender, and these classifiers can discretize the output distribution, the synthetic data sets, into different bins. And so we can do a similar thing with the density plots, except these are more broad bins, to see which data set is the most diverse. On the top, we have Flickr Faces HQ, the training data set for the generator, the StyleGAN2. And we see that there's this really stark contrast in skin tone, in age, and it's more balanced in gender. In StyleGAN2, just randomly sampling from the generator, we see that it inherits these biases. So we see that the proportions are nearly identical. When we sample using an optimization algorithm like quality diversity, we're able to get a higher spread again. And this is sort of promising because it verifies that we are getting a higher spread, and it's not just a clip that's making it appear like we have higher range of concepts. Of course, this result would likely not be applicable to measures of diversity that aren't specified during optimization. So remember in step 3 how we consider different measures that we might care about, such as skin tone. If we don't specify those in the optimization process, it's not super likely that the outputs will be as uniform. And again, it's a pretty big challenge to think of an exhaustive list of all the concepts that need to be balanced for any particular application. It remains open challenge to try to get these synthetic data sets to be as balanced as many concepts as we might care about for training. Next, we looked at how these data sets would perform in pre-training. So we pre-trained using these data sets, and then we trained on Costio web face. And we looked at how these classifiers would perform on test sets partitioned on faces with dark skin tones and faces with light skin tones. Without any pre-training, we get about 88% accuracy on dark skin tones, 94% on light skin tones. And when we train with randomly sampled synthetic data, there is an improvement across the board, but there wasn't really an improvement with fairness. We see that the disparate impacts ratio, which is the ratio of performance of dark skin tone performance above light skin tone performance, there's not really a substantial difference. When we pre-train using quality diversity, we see the same increase in light skin tone. We achieve the same performance, but an elevated performance in dark skin tones. So there is a sort of noticeable difference for faces with light skin tones. Although this difference isn't super big, I think facial recognition is just one of those tasks that it's really difficult to figure out what sorts of data are really helpful for improving performance and making sure that our models are fair. And that's why this project is so challenging, but also this issue is so important. Finally, we looked at how the classifiers performed on traditional test sets that aren't partitioned on skin tone. We looked at labeled faces in the wild, and then there's some for pose, like they have more balancing across like faces of different poses, of ages. While classifiers trained on synthetic data improved in accuracy compared to those without any pre-training, there wasn't really a noticeable difference between whether like the random sampling or quality diversity was able to improve performance, which it's also sort of a interesting result because it shows that we're able to get an increase in fairness without the expense of lower accuracy, which sometimes that's a trade-off. But it's at the same time, we aren't getting like a huge improvement in accuracy, which intuitively kind of makes sense. Our objective here is to balance out the synthetic data set, but there might not be like substantial differences in quality. Okay, I want to touch on some of the limitations that of this type of method. We've been discussing a method to improve uniform representations, and while uniform representations are helpful to battle underrepresentation of some underrepresentation, some tasks might actually benefit more from proportionate representations instead. For those types of tasks, I would probably recommend like you might find some middle ground between uniform representations and the real distributions, which might be more modal. Secondly, we express our measures using text prompts, which are subject to linguistic biases. And as we saw with the associations between skin tone and gender presentation, these can affect the type of data that's generated. We also saw some interesting linguistic biases based on the text that was used in the objective function. I think I tried like photorealistic for one of the pilot experiments, and like the images came out with sort of like a more airbrushed artistic quality. And after reading it into it, photorealistic is more used in to describe art rather than photos. Finally, because QDGS doesn't learn or modify the parameters of the generator, it still assumes that the desired concepts are represented to a sufficient standard in the data used to train the generator. So if this isn't the case, QDGS won't be able to find solutions that create the desired outputs, right? If Flickr Faces HQ doesn't have anyone with a orange top hat, it might be kind of difficult to create that sort of data from the generator. Okay, I'll leave you guys with takeaways. We use quality diversity, a type of optimization algorithm, to try to balance synthetic training data sets for using for training downstream classifiers. Our measures are able to be customized in text prompts. So if you move this to another domain, you can customize the text prompts for the concepts that you care about. It's kind of nice that you're able to do this without a specific classifier like in some other works, because you would have to have labeled data to train the classifier for the specific types of concepts that you might care about and want to optimize for. We also find that compared to random sampling of generators, we're achieving a higher fairness improvement and similar accuracy improvements compared to no pre-training with synthetic data at all. And yeah, that's sort of it. The code to reproduce our work and additional results are described in the paper. That's sort of all I have for today. I'd love to be able to answer any questions.
Okay, Alan. So Zara kicked us off with a question. Zara, did you want me to go ahead and ask the question that you have in chat, or did you want to come off mute to ask your question? Okay, Zara had a question in the chat. The question was, who determines the text that goes in, and how can that person, check their biases in that respect? I'm not sure if this is relating to prompting or training, but that was the question.
Yeah, so it depends on the generator that you're working with. The generator that we've been working with is StyleGAN2, and StyleGAN2 maps from latent space, so it's just a real valued vector. It's not like Stable Diffusion or DALL-E where you start from a text space, although increasingly it seems like generators are starting with from the language modality. The text that goes into QDGS is determined by the person who's trying to create that data set for pre-training. So this might be like a ML engineer, this might be the researcher. It's sort of the practitioner who cares about what the downstream classifier is doing. And you can try to modify different text based on what the output looks like. And to answer your second question on how to check for the biases, it's a really tricky question, because in order to check for biases, you sort of need to have a test set that is more balanced and unbiased. So it kind of becomes just like, what comes first, chicken or the egg? I sort of recommend validating it or looking at inspecting it manually. So looking, if you're working with image data like facial recognition, looking at the images that are produced and looking at what those proportions might look like, sort of looking at the density plots that we did that we looked at earlier, and seeing whether like we're over generating one particular part of the measure space over the other.
Okay. So yeah, I had a quick question, at least in terms of the limitations that you mentioned. The second one was, text prompts should be carefully designed to avoid linguistic biases. In terms of QDGS, was it tested with any other languages or character sets outside of standard English that might even have different or variations of a linguistic bias?
Yeah, that's an interesting question. We didn't try different languages. We only tried English, and a large reason why that is the text encoder we're using, Clip, it was trained primarily off of English text.
Okay.
So we want text that is best represented in CLIP's latent space. We want text that best is able to describe the images that are going on. And if you're working with Japanese text with CLIP, which it might not be as familiar with, it will definitely struggle more to describe the images as well. And then you might introduce more biases. So you're exactly right. If we're using different languages, the outputs that come out might be more incoherent.
Okay, that makes sense. We don't have any additional questions in the chat, but if anyone wants to raise their hand and or come off of mute, please go ahead and ask your questions. And I know you probably have a couple, Benedict, as well.
I don't have any. I don't have any.
Okay. So I did have one more question then, Alan. I'll go ahead and ask an additional question. Let's see. I had written it earlier after I read the paper. But yeah, my question was, what potential limitations do you foresee, in using QDGS when you're scaling up to more complex or higher dimensional data sets? Data sets that are, even beyond facial recognition or shape classification. So what issues do you see when you get to data sets that are a little bit more complex?
Yeah, that's an interesting question. I think particularly with tasks that might be more open-ended, the difficulty lies in designing an objective function that is able to describe all the quality attributes that you might care about. And similar with single factor optimization, if you're maximizing a single objective function, you might get stuck in these minima that constrains the data that you end up with. So you still have this sort of trade-off between exploitation, quality, and diversity, right? So in order to design an objective function that accurately describes whatever you care about in this particular task, that is a challenge. The other limitation that comes to mind to me is it also you rely a lot on like the generator's what data the generator has seen, right? So quality diversity, it's able to exploit the learned parameters within the generator. So if it's seen some data that you might care about, you might be able to create that sort of data in your synthetic data set, your outputs. But if you've only seen apples and you're trying to create oranges, it'll really struggle because the generator hasn't seen that type of data. So it's really, QDGS is really just a tool to try to help balance the data sets you're creating with generators on a data set level.
Okay, that makes sense. Okay, we have another question from Mayank. Did you want to come off of mute, Mayank, to ask your question? Okay, can you see Mayank's question in the chat, Alan?
Yeah, I can see it.
Okay.
So Mayank asked, what about using diffusion models instead of autoencoders? I suspect that they may not be as performant, but might serve the job as well. So one of the, we didn't test on any diffusion models, but quality diversity, it doesn't look at the model architecture itself. There's different types of optimizers that are either differentiable or not. So even if the generator is black box, we're able to look at the images and run quality diversity with a different non-differential optimizer to get the types of images that we might care about. Empirically, I haven't done the experiments with diffusion models. I suspect with larger, I don't know that there will be a difference based on whether it's diffusion or a GAN or an autoencoder, but there might be other factors relating to the architecture that might be affects the performance more, such as the size of the model and the type of data that it was trained on. That's my suspicion.
Okay. Benedict had a question for you. Do you see that one in the chat, Alan, or did you want me to read it out to you?
I can read it out loud. Okay. Do you think perhaps multimodality can be employed to improve diversity? That's an interesting question. One of the things that I liked about this project was I was able to work with text as well as or text to describe images, and I think like working with two modalities, it sort of elevated like the creativity I was able to use in creating the synthetic data sets. If I was just working with classifiers as my measure functions, I would have to have like a labeled data set of skin tone, a labeled data set of facial pose, a labeled data set of XYZ, and it's more difficult to do those things only in the image space as opposed to with two modalities. So in certain ways, multimodality can improve diversity because you're better able to express what you might care about in language. At the same time, there are issues that come with it, linguistic biases. But overall, I think the pros are better than the cons, and I do like the idea of like multimodal models being generally larger, and there's larger latent space to be explored with quality diversity. So it's possible that we can create where we have less of a constraint when we're trying to sample for interesting synthetic data.
Okay. Okay, so Alan, there are no more questions in the chat, but I'll sneak in one more question. So, so what does the future hold, at least as, from your standpoint, in terms of, this type of research in the future? Are you planning follow-ups to this paper or maybe additional research with new papers at University of Pennsylvania regarding this topic?
Yeah, I think there's a lot to be done. I think trying to sample for synthetic data that is diverse and original is a very difficult task because at its core, it's sort of like performing magic, right? We're trying to create something that is better than the data that it was trained on. And it's a really difficult space. One of the questions that I am beginning to become more interested in as I discover more areas of research is how we can get language models to better understand social concepts such as social norms, moral values, and these things are rarely captured in real data sets online because these data sets are often static and they're not really interactive. And these kinds of things mostly come up in interactive settings. But as we move forward into the future, a lot of the interesting applications between humans and machines are going to be interactive. And so I think trying to learn these concepts that are not sufficiently represented in real data is a really interesting question to me. So I'm beginning to look at these questions more in the language space.
Okay. Okay. So any other questions from anyone for Alan before we close off the call? Okay, Alan, well, I think we've gotten through all of our questions today. So this was really a very informative session today. So we really appreciate your time. And what we'll do as well is we will make the presentation available on YouTube. It should be available within about a day or so. And we'll send a link to you, Alan, and everyone else who was on the call so that, you can reference the session later.
Thank you so much, Hamid. It was a pleasure.
Okay.
It was a pleasure talking to everyone.
Okay, thank you, Alan, and enjoy your time in Spain.
Thank you so much. Bye-bye now.
Okay, everyone have a great day. Bye-bye.